Okay, so to get going, we'll start the actual workshop now. Enough of the entertainment. My name's Dave Nielsen, I'm with Intel, and I've got with me Tim from Elephant Scale and Alex, actually with Seismic. And together they're going to put together present a workshop on how to get started with image recognition and deep learning with Spark using BigDL, which is a framework that adds deep learning capabilities to Spark. Now, just high-level stuff, you might ask, well, there's other frameworks out there, why would I use BigDL, why would I use Spark? And at a high level, you should think about Spark as being a data processing framework. In fact, it's a distributed data processing framework. And what that means is that you can take advantage of a cluster of servers, and you can send your data out to large numbers of servers, and then you can take your deep learning algorithms and send them out to where the data is, and then crunch all the data on many servers, which gives you a lot of power. And that gives you, especially if you already have a company that has data in some sort of data warehouse or data lake sitting on HDFS, and so you already have maybe Hadoop, and then you have your Spark cluster connected to that, so you can automatically bring in your data from your Hadoop. So you've already got your data there. If only Spark had a deep learning library that you could add to Spark to give you deep learning. Well, that's what BigDL is. Okay, it's written in Scala, and all you do is add it. It's just a library that you add to your Spark jobs, and now you've got the ability to do deep learning in a distributed fashion. So if you've got a cluster with, say, 32 servers, that's a lot of power. Okay, you can crunch a lot of data with that. Why don't we hold our questions for later, okay? So what we did is we put together this workshop. And what I always tell companies to do is if you have a Spark cluster, then why not just simply take this library, it's free, it's open source, nobody's ever charged for it, and add it to your cluster, and then now you can tell your data scientists in your company, hey look, you've got access to deep learning now. There's nothing stopping you now. You can do deep learning. And it's got most of the architectures and algorithms and models that you might have in other similar frameworks. So there's really no reason to not use it. So this workshop, I'm really happy to introduce you to Tim Fox. He's with Elephant Scale. Alex will come up a little bit later, and they're going to give you first go at a workshop that Elephant Scale has been giving, and then Alex will follow it up with a workshop on image recognition using BigDL that he has created. So,
Great.
Tim, take it away.
All right, thanks. All right, welcome everyone. So a few logistical things. So here's my contact information. I'd encourage you that if those of you who have laptops or other devices that you can go to the Adobe Connect, elephantscale.adobe-connect.com/structure.2017. And then you can actually just enter as a guest for that. So enter as a guest. Also, to go ahead and register for the PDF to be sent to you, you can go to trainingroom.elephantscale.com/student/register and enter this code, and that will get you these materials sent to you. And we also have a GitHub here, github.com/elephantscale/BigDL tutorials. So go ahead and make use of those as well. So you may want to take a picture of that, at some point. So. Good. So, all right, let me go ahead and introduce myself. So, again, I'm Tim Fox. I am a data engineering, data science practitioner. I'm focused on big data, deep learning, machine learning, etc. The company I work for, Elephant Scale, we do training, seminars, workshops, consulting, and many other related things. We have a special focus on data science and big data and including deep learning, machine learning, etc. I also am the author of a data science course on LinkedIn Learning. So that's a little bit about me. I've been working with machine learning for a number of years now. Actually, when I was a student, I actually worked on computer vision, and I also, in my career, I worked in a number of different applications in the areas of big data and in terms of machine learning. One of my earlier projects actually was I worked for the oil and gas industry, and we were looking at volumetric geophysical data for finding oil and gas. And so we're using self-organizing maps and neural networks algorithms for that. And so when I discovered the Hadoop framework, one of my first thoughts is that, hey, this would be a great platform for distributed machine learning. And so that's been a big focus of mine, is machine learning and deep learning on big data, and the Hadoop and Spark framework sort of fit into that. So now kind of quick survey here. So I kind of want to understand, what everyone's doing. How many of you are familiar with kind of the concepts behind deep learning, and maybe you used a framework like, say, TensorFlow, Caffe, Keras, etc.? Raise your hand. MXNet. Okay, so maybe looks like maybe a little bit less than half of you have some familiarity with that. That's excellent. And so now, how about on the big data side? BigDL, actually, we're going to talk about, runs on top of Apache Spark, which itself is part of the Hadoop ecosystem. So how many of you are familiar with Apache Spark and or Hadoop? Okay, maybe about the same, maybe a little bit less than half. Great. Well, that gives, I know that some background. So I'm going to give a quick overview here of AI and machine learning and deep learning. So now AI basically is a very general category which just talks about machines being able to carry out smart tasks. So that can be in a lot of different ways. Now, machine learning is a specific type of AI which allows software to learn without being explicitly programmed. And normally when we think of machine learning, we think of a lot of statistical methods and other things like that. Now, deep learning is a subset of machine learning in which we use neural networks specifically to solve some hard problems. So some applications that you're probably familiar with are things like self-driving cars, using machine learning systems for image recognition. Face recognition is something Facebook is working on a lot. Their deep face product is designed to do automatic face tagging for uploaded photos, etc. So that's done using deep learning models. So now, deep learning has a really long history. So I think I was in university quite a while back, and we were working on neural networks and deep learning even back then. But there's really come into its era now. Back in earlier times, compute power was insufficient for the time. Training data sets were often insufficiently sized, and we lacked the ability to parallelize our work. So now, what we have today is we have a number of things that come together to make deep learning successful. One of those things is big data. Deep learning algorithms will often work well in the absence of a lot of data. And so also we have an ecosystem around big data. So we have platforms like Hadoop, Spark, NoSQL, etc. have created sort of open source ecosystem, an open source stack that I know many of you have said you're familiar with. I've been working on that stack for a while. And that has been used in a lot of places for providing a standard big data framework that we can then build applications on top of. And another thing is big compute, right? And so cloud has significantly lowered the cost to massive compute. And so, of course, here at Structure, we've been talking all about that. So now we have that, the cost of this compute is constantly falling, and the agility that we can get by, for example, just starting up a 100-node cluster for 5 hours in a transient workload like that, that gives us huge benefits in terms of being able to scale our deep learning. So now, in machine learning and in deep learning and AI, there's an ecosystem behind that too, right? So in various languages, for example, in Java, there's machine learning libraries like Weka and Mahout, and also in terms of deep learning for J, you may be familiar with. I think we're all probably familiar with Python, scikit-learn, right? And so, and then in deep learning, TensorFlow, Theano, Caffe. R, of course, has many libraries in the areas of machine learning and deep learning. And then as far as distributed machine learning and deep learning, there are frameworks like SparkML that we're going to be talking a lot about now. Also H2O, and of course BigDL that we're going to be introducing today. And of course cloud, the various cloud vendors, Amazon, Microsoft, and Google have pre-trained models, ML APIs, and other kinds of distributed ML frameworks as well. So now one of the challenges on machine learning, and this is one area that's particularly of interest to me, is that a lot of libraries, like scikit-learn, for example, are outstanding, in terms of functionality, but primarily designed for a single node. So you on your node, and not really designed to take advantage of a cluster. So now, in recent years, we have frameworks like Spark ML, H2O, and many others designed to take and distribute machine learning algorithms at scale on a cluster. So, some modern deep learning frameworks that you're probably familiar with, I've mentioned some of these names already, TensorFlow, Keras, Theano, Torch, MXNet, Caffe, etc. So, now for scalable distributed machine learning, tools like Spark ML are one theory, and that's one, BigDL that we're about to talk about is built on top of Spark. So Spark ML, if you're not familiar with it, is a cluster computing framework which is designed for big data. It also has a lot of in-memory and caching capabilities, and has language support is written in Scala but supports Python, Java, R, in addition to Scala. Of course, we've already talked about TensorFlow. It has it runs on CPU and GPU especially, and also on custom silicon called TPU. There are also cloud-based scalable machine learning like Google Cloud ML, Amazon ML, Azure ML Studio, etc. So there's a number of scalable machine learning frameworks based on public cloud like that. All right, so let's introduce BigDL. So now, BigDL is a distributed deep learning framework for Apache Spark. So, you may be familiar with, because we talked about the whole ecosystem of deep learning, and I'm very much supportive of all of these tools. I use them myself, and I'm not here to tell you anything bad about those. However, the point of BigDL is to bring, kind of massively distributed deep learning. Now, feature-wise, BigDL is designed to be feature parity with other popular deep learning frameworks like TensorFlow, Torch, Caffe, etc. And so the same types of models that we can build in those frameworks, we can also build in BigDL. As a matter of fact, what we'll talk about is that we can actually export models from TensorFlow and Caffe, etc., and import them into BigDL and vice versa. So we also are developing support for using BigDL as a backend for Keras. So again, they're integrated with that broader ecosystem to try to have similar features. The performance is going to be powered by Intel's MKL and multi-threaded programming. So also, we're going to use Apache Spark in order to scale across up to thousands of nodes on huge data sets. And it's an open source framework. It was released back in December 2016 and recently just came out with version 0.3. So BigDL runs as a Spark application. So Spark actually is a host for a number of other types of processing, including Spark SQL, Spark MLlib, Spark GraphX, and there's other Spark components that are there. BigDL sits alongside those, so we can use Spark's in-memory compute capability. Spark has a massively distributed in-memory file system called Alluxio and Tachyon, and there are many other features of Spark that we can use for that and integrate with other Spark components. Also, we have the ability to do easy development using BigDL, and we're going to show you how we can even do that with Jupyter Notebook, which I'm sure many of you are familiar with. Now, comparing BigDL and, say, TensorFlow, but the same thing could be said for many of the other frameworks as well. So again, some of the comparison and differences, BigDL is built on top of Scala with a Python front end, whereas TensorFlow is a C++ engine. We'll talk about CPU versus GPU in a future slide. Hadoop compatibility, BigDL is designed to run natively on Spark and Hadoop, whereas TensorFlow and many other types of frameworks tend to access Hadoop data only as a client. So it also is going to rely on Spark for massive distribution. One of the areas of development right now in TensorFlow is how we can develop instrumentation for doing massive distribution of TensorFlow. We both run TensorFlow models. Of course, TensorFlow runs that natively. And so the summary here is that BigDL is going to be excellent for doing distributing machine learning models at massive scale on big data. Whereas TensorFlow, of course, is an outstanding library, but is going to be better suited for small and medium scale data where parallel processing is not a major concern. So, now, BigDL is going to give us big compute plus big data. So, big compute is going to be fast linear algebra, Intel MKL library, while as big data concerns are going to be I/O parallelizability to run on many CPUs and on many nodes for distribution. Going to give us massive scalability. So we're going to run Spark. They're going to be part of the Hadoop ecosystem via Spark. Yes, question?
Hey, what is MKL?
MKL is the Intel math kernel library, I believe. So it's basically it's a library produced by Intel to allow developers to have numerically intensive work like linear algebra and other things like that to be optimized to run on supported Intel CPUs. So.
And BigDL comes out of Intel as well?
That's right. Intel is a sponsor of BigDL. Although I don't work for Intel, neither does Alex, but nevertheless, it is actually sponsored by Intel, and a lot of the key contributors are Intel employees. Yes. So yes. So we talked about now Hadoop is, if you're familiar kind of with the big data ecosystem, Hadoop is kind of the big data platform. So in terms of all other kind of parts of the big data ecosystem, Hadoop is kind of the oldest and kind of the lowest common denominator for all of them. And so the fact that BigDL is able to run on the Hadoop ecosystem via Spark is a huge advantage because that's really where most of our big data sets are. Is that our large data sets are primarily within that big data ecosystem. It also plays nicely with other with other frameworks like we can use TensorFlow and Caffe models at scale. We can also train new models based on our existing TensorFlow or Caffe models. Okay, so one of the things that has a lot of people excited today, including me, is the fact that GPUs have, especially on frameworks like TensorFlow, have enabled very high performance for deep learning. And so now, in the past, CPUs have not been very vectorized for parallel compute. So that means is that we've traditionally been able to see about an order of magnitude faster performance on GPU-based compute versus CPU in the case of deep learning and other kinds of linear algebra type of tasks. So now, Intel, of course, has a motivation that they would like to see CPUs be able to be at least competitive with GPUs in terms of overall performance. And so modern CPUs have developed vectorized linear algebra operations that are designed to approach the speed of GPUs when properly optimized and also offer faster I/O performance for big data. So the Intel Math Kernel Library is designed to give highly optimized, threaded, and vectorized math functions that are going to allow us to have high performance on CPU-based approaches. And Intel provides C, Fortran, and other APIs for compatibility with common APIs like BLAST, etc., for linear algebra, LePac, FFTW functions. And this will integrate with other libraries like, for example, NumPy and SciPy, etc., Python that use those under the hood to allow that to be accelerated. And also, this is going to mean that we can deploy that code automatically without the need to branch code. So, this is a slide directly from Intel, but you can see that properly optimized with the math kernel library, you can see much higher performance. It's actually talking about Caffe rather than BigDL, but the same thing is there in terms of about an order of magnitude better performance there, approaching the speed of GPUs. So GPU-based acceleration is definitely excellent for small to medium-sized data sets. So now, so that means is that when you have a relatively small number of nodes, we definitely want to go for GPUs because GPUs are going to give us a level of parallelism that we can't necessarily do in a single GPU. But if we have massive clusters and massive data, then in those cases, CPU is actually much better because in that case, we end up with the problem of sometimes too much compute in the form of GPUs and not enough I/O bandwidth in order to actually feed that to them there. So remember, in big data, we have not only kind of a compute-bound process, but we also have an I/O-bound process as well. And so the big compute versus big data trade-off, and when we deal with thousands rather than, say, hundreds of thousands rather than dozens of nodes, and if we're also dealing with petabytes of data distributed on all of those nodes, then the machine learning part has to be part of a bigger piece of the puzzle. And so the fact is that our data systems are pretty complex. They have a lot of moving parts. And as exciting as deep learning and machine learning are, and they are very exciting, I mean, that's why we're all here in this room, right? Nevertheless, the overall infrastructure that we have in terms of handling our data, the ML piece is actually a fairly small piece right here. And so the other parts we have here, for example, are the, the configuration, data collection, feature extraction, verification, other types of infrastructure, serving and monitoring tools, etc. And so these are often already in place. For example, many of these tools are built on top of kind of part of the Hadoop ecosystem, right? So where we have that, the ability to build pipelines for our data, to be able to develop, have metadata repositories, and data transformation pipelines, data serving pipelines, all these kind of things that the big data ecosystem has been working on now for, 10 to 15 years, right? So all of that data comes together, and that provides an outstanding platform for doing this crucial piece. But this piece, in many ways, is not really even possible to do without kind of the data engineering infrastructure that goes around that. And that's kind of part of what the motivation behind BigDL is that we want to bring deep learning to where the kind of the environment and the pipeline that the data actually is, right? So it is outstanding, if we can go and extract some data for there and do some deep learning kind of independently. That's good. But even better is if we can take and go to kind of our existing data workflow or existing data pipelines and start doing some deep learning as part of it. So BigDL is designed to give us big data plus deep learning, which honestly, before BigDL, there's been a big gap in this area. Of course, we have pretty good traditional ML frameworks that are built on top of our big data stack. So things like Spark ML plus H2O and other kinds of traditional ML, and we can do things like ensemble decision trees. We can do other kinds of traditional ML, right? And that's all great. I mean, we can still continue to do that. On top of that, we also have great deep learning libraries too, like TensorFlow, Theano, Caffe, Torch, etc. But those are not particularly well integrated with the big data ecosystem. So that's the big gap that BigDL is trying to fill. And so now, in terms of big data, we want to be able to send our compute to the data. So that's kind of, if you're familiar with the Hadoop ecosystem, that's been kind of the mantra of sort of big data for the last 10, 15 years, right? Instead of our traditional model where we have kind of our code or processing stationary and our data in motion, the big idea kind of that sort of launched the big data revolution is that you have your data on a cluster and then you send whatever processing you want to do on that data to there. Because again, your code is going to be in maybe megabytes to gigabytes, whereas your data is terabytes to petabytes, right? So which one do you want in motion? You want to have the code in motion and the data stationary. And that's the model that BigDL is trying to build on top of. So it uses what we call data locality. And that, in other words, is that you're going to have the best system performance in a big cluster of up to thousands of nodes if you run your processing on the same node that hosts the data. So, and also we're going to be able to use cluster managers like Yarn. That's basically the Hadoop cluster manager that's been around since time immemorial. And other ones like Mesos, etc., which is also supported by Spark as well. Okay, and so some of the use cases that we can see with BigDL, we've already talked about some of them. Do things like fraud detection, sentiment analysis, many other types of use cases we have available here. And we have some use cases example of this URL here. That's an Intel URL, the analytics zoo here. So, okay, so how do we run BigDL? So, again, a lot of you may already be running Hadoop/Spark on your clusters in your enterprises, right? So for you, I mean, it's great. You can definitely go to start developing and deploying BigDL in your environment. But before you probably even get to that, you're going to want to be able to develop on BigDL. Again, how do we do this on your laptop, say, or how do you do it on, say, a cloud instance? You won't really be able to do big data on your laptop. But again, as you start to get familiar with the framework, you need to be able to do that. So there's several options that we have available, and this is some of the things that I'm personally working on, is things like, for example, a Docker container that we're developing, as well as a VM sandbox, and as well as a cloud-ready AMI that you can deploy to AWS. So, all right, so what I'm going to do for the rest of my talk before we welcome Alex is I'm going to demo quickly what BigDL in action. Well, and I'll show you actually a little bit about what our options are for the development sandbox. So first, actually, let's talk about, so I'm going to demonstrate here Docker and the sandbox VM. So I'm actually going to be running my code examples on a running Docker. And so how many of you are familiar with Docker? Like, is pretty much everybody, I think pretty much most of you, right? So you're familiar kind of with the concept of containerization and all that. Great. So we actually have, let me, what is this? Okay. So we actually have let me get a browser window open. Okay. Give me a second here. Okay, so actually if you go to dockerhub.com/elephantscale, let me go here. So we have actually, that what we've been working on is the, usually hub.docker.com, and it is the elephant scale. Okay, so the elephant scale BigDL sandbox. So this actually here, I'll just paste this here. There, and actually you can get that by calling, I'm just going to write this here, Docker, let me move this over a little bit so you can see it. Docker, so if you do Docker, pull elephant scale. So I wish I could have you guys actually do this now. Unfortunately, the sandbox is like 10 gig. So if we all do it all at the same time on the internet here, that's probably not going to work. So that'll have to be more of a homework exercise for you guys. But I encourage you to do that. Now, Docker is going to work well for some of you. If I'll just kind of say that, especially Mac and Linux users, you shouldn't have any problem with Docker. If you're running on Windows, I think there's some specific requirements for Docker. It runs best on Windows 10 in the Pro version, which has Hyper-V running on it. So if you're not in that environment, you may prefer the sandbox VM, or otherwise you may actually prefer that. So let me just quickly go over the sandbox VM. So the sandbox VM is elephant scale. So if you go to our website, elephantscale.com/sandbox, we have a VM which you can download. So let's just write that here. So elephantscale.com/sandbox. So we have here you can actually download this here, and there's actually a link here, and you can import that into VirtualBox or VMware. That will get you up and going. And so, and again, this that may be the quickest way for those of you who are running certain versions of Windows, etc. Again, go there, or in other words, you may prefer that. So basically, it's just a Ubuntu image that you can go ahead and there with BigDL already set. Okay, and we have that there. So let me actually show you the BigDL in action here. So I have that. I actually have the Docker here currently running on my Mac. So and so as I run that, actually it immediately will start up and run Jupyter Notebook, and Jupyter will be already configured to connect to a running Spark, a local Spark image, and then we'll be able to do. We'll be able to do Jupyter notebooks that involve running there. Of course, now I don't have to do everything in Jupyter. I could go ahead and write my own Python or Scala code and go ahead there, but I'm going to demonstrate this using Jupyter. So, all right, so what I'm going to start out doing is I'm going to show you a couple of the ways that we can do this. So now, and the first one I'm actually doing is this one called feedforward iris. So now, there's a data set you might be familiar with called iris. You know, it's basically a simple data set that's kind of a hello world of classification. And so basically, you kind of give different dimensions of a flower, and then you go ahead and try to identify which species of iris it is, right? So, sure you've all seen it before. Okay, so now this is Python. So all my examples are actually in Python, We also, of course, BigDL also supports Scala as well, although I know many of us in the data science space are more familiar with Python, and so that's fully supported in both Spark and BigDL as well. So what we see here is that you can see I'm importing a lot of my classes here from BigDL, and I have that here. Now, there's a couple different things I'm going to show you. The first example I'm going to show you is using the RDD API, which has more features. And so that is, I'll show you kind of how we can do that with the RDD API. We have another API, which I think is really cool, which is a data frame-based API that is going to integrate with the Spark ML framework. So let me just go ahead and show you this. So this is the RDD API. So first I'm going to set some parameters here. So this is going to be, I'm setting my learning rate, my training epochs, my batch size, my display step, etc. And then I also have my network parameters here. So for Iris, I have 4 inputs because it's petal width and length and sepal width and length. I have 3 classes, Setosa, Virginica, and Versicolor. And in this case, I'm going to have a hidden layer with of size 3. And I actually have something here where I try to figure out, we're using some rules of thumb, what my hidden layer should be, and so I won't go into that now. So now, if you're familiar with Spark, this will probably look familiar. I'm just going to read some of my data into in this case into Spark data frames. So that's where the spark.read.csv is. So I do that. Then I'm going to do a few visualizations here. I'm going to plot here how many of each training class I have. So you can see there's roughly similar numbers of frequencies of the training class and the Iris dataset. You have Setosa, Virginica, and Versicolor there, and you can see that. And in terms of the validation class, it looks like we turned out with a bit more on the Setosa, but again, fairly balanced and the way that worked out. Okay.
So,
question? Yes.
yeah, are you saying, so you have the labeled initially and then you're validating through the
Yeah, so what I just did actually is that we're loading, we have our Iris data set. I think it has 150 samples. So we split that up already into training and test. So I think, in fact, the data set just, I think, comes that way. So it comes split up into training and test. So the training is what we're going to use in our training step. And of course, we're going to measure our performance on our algorithm based on the validation data. And that's a very typical kind of supervised machine learning way we go. Again, we're talking really kind of basic sort of hello world kind of stuff. There's some more advanced ways of dealing with that, but that's what we're kind of dealing with here. Yeah. So, okay. So if you're familiar, I now have my data. I've gone through. This is what it looks like. Again, I just have my 4 dimensions plus this last one is the label. So, okay. So now I'm going to go over in the next data set how we can actually integrate with Spark ML pipelines. This is actually showing using the RDD API, which RDD again is if you're not familiar with Spark, is kind of more like an array than like a data frame object. So it's a kind of more classic Spark API. So here actually I'm going to be converting my input rows from my data frame into the format that BigDL likes to see its data, which is called the sample. There's a class called sample. So I'm going to create this RDD of type sample here. And so whenever you do this for your data, if you look at my here, you can actually kind of follow a similar pattern for if you're going to use the RDD API in order to put that in terms of RDD of sample, which is what it wants to see. So then once I do that, again, now you can see here I have training 120 and test I have 30 rows, so 150 total. Okay, so now I'm going to set up my neural network. And so here what I'm doing is I'm going to have I'm going to do a single hidden layer here, and I'm going to, so you can see here I'm having a linear layer with ReLU activation. So those of you who are familiar with a neural network, so that should mean something to you, I hope. And then also, since this is a classification model, I'm going to have a final layer, which is going to be a softmax layer. So that softmax layer is going to basically take my output and allow me to have, in this case, I have 3 output classes, right? Okay. So real simple network, I have an input layer, I then have a hidden layer, and I have my softmax layer because it's a classification, right? So now I'm going to take that, you can see here that it goes and it creates my various layers. Okay, now I got a train. So now what I'm going to do is I'm going to set up here my loss function, a class NML criteria, and my optimization for AdaGrad. So what I'm going to do here is I'm going to set up my optimizer. I'm using I'm specifying my learning rate here. I'm specifying my training epochs. All that was set up at the top of the script, if you remember. And then I'm setting my validation logic here, again, specifying my batch size, my validation API, my validation RDD, etc. So then I'm going to go ahead and run this. I'm going to actually save this here to a location, which this is actually important because I'll be able to use this to load TensorBoard. If you're familiar with TensorBoard, it's a visualization tool for TensorFlow that we also support at BigDL. So I'm going to save that. By the time I'll actually load up TensorBoard. So then I'm going to run it. You can see here, when I run this, it took about 10 seconds to train my model. Okay, so now I'm actually going to plot the training graphs. So here we can actually look at the loss and the accuracy. So at the end of the day, we're seeing the loss go down, although it bounces around a fair bit, and we see the accuracy going up. So that's good. So we can also see the visualizations on TensorBoard as well. So we can go and load TensorBoard there, and now since I saved my folder here in temp BigDL summaries, then we can go there as well. Okay, so then I'm going to show my accuracy in my confusion matrix. So what I'm going to do here is I'm going to get my predictions. So I'm going to call train model.predict on here. And I am then going to go ahead and get my predictions. I'm going to then calculate my accuracy and generate a confusion matrix. So we can see here in this case that the accuracy I got here was 96.67%. So I think in the data set, I think we got, if we look at the confusion matrix, I think we have one misclassification in this case. You can see that over here. So there's our misclassification. So then that is it. So you can see here, Iris on BigDL using the RDD API. So any questions on what I just showed you? Yes?
Are you assume TensorFlow is
I'm sorry, you asked
do you
me?
assume TensorFlow is running because
So,
you are not using that?
oh yeah, I mentioned TensorBoard doesn't necessarily...
I know that, but without TensorFlow running, can you have TensorBoard?
Yeah.
Yeah.
So
Yeah.
TensorBoard is installed together with TensorFlow. But basically all the TensorFlow files just going to sit there, you're not going to use them. And in fact, there is a separate, you can find somewhere where you can get a TensorBoard standalone. So TensorBoard is basically a program independent from TensorFlow entirely. It simply runs, understands the log files in the format, in a certain format, and just provides this web page where you can see the output.
Yeah, it's actually really cool. And actually we don't need the, I'm not sure if you can install TensorBoard totally independently. I think if you say pip install TensorBoard, it'll probably install TensorFlow too. But nonetheless, again, we're able to integrate with that. It's good to have TensorFlow as well because we can interchange TensorFlow models with BigDL models and vice versa. So good to have anyway. So, okay, any other questions? Before I look at Alex, I actually want to show you the pipeline API as well in another notebook. So how are we doing on time? Actually,
Fine.
Okay.
More minutes.
So let's actually show that. So I think actually this, this is probably going to be the API that we'll use most often, the RDD-based API, because it is the most flexible and has the most features. But I am going to show you the integration that exists here with the pipeline API. So now, if you're familiar with Spark as a framework, so Spark started out with the RDD, which is basically like an array or a collection, and then Spark has since moved into a higher level object called data frames and data sets. And most of Spark's newer frameworks tend to be based on data frames, right? And ML is no exception. So actually ML in Spark has been totally overhauled in version 2.x. And so now we kind of have a pipeline-based system in ML. And that's actually one of the coolest things about the Spark framework, in my opinion, is this very flexible, very reminiscent of sklearn, if you're familiar with that. But unlike sklearn, of course, scalable and distributed. So that framework instrumentation is really cool. Unfortunately, there's very minimal functionality within Spark ML Live in terms of deep learning. There is actually, you can do some very simple feed-forward networks, but that's it. So being able to integrate with that, kind of is a perfect complement in a lot of ways. So, okay, so I'm going to talk this here about same data set, so I won't go over to that anymore. So what we're going to do here is I'm going to show similar parameters here, right? So we have, again, talking about the learning rate, again, the size of the network and all that, and sizing the hidden layers and all that, right? So now we're going to load the data, and now, but instead of actually starting at RDD, what we're going to do is we're going to actually set up a Spark ML-like pipeline. And so what we're going to do is there's a class here called Vector Assembler that we're going to use in order to extract the features. And then we're also going to, the next stage of the pipeline, we're going to go in and use a, let's see, we're going to go ahead and use a standard scalar right here. Here's a standard scalar. So that's going to normalize our dimensions. And we can do a number of other things. If you're familiar with Spark ML, there's a number of other kind of data science related tasks that we often do in our pipelines. Our pipelines in real life can get quite deep, actually. And the pipeline architecture of Spark ML, the 2.0 version, is really cool that we can integrate that. Now the coolest thing of all is the fact that we can then take BigDL and plug that right into the same pipeline. So, so that means, so here I'm showing, here's so what I've done here is I've actually created a column here in my data frame called features. This is how we normally do it in Spark ML. We create a feature vector plus a label. And then what we're going to do now, though, is that normally I might do in Spark ML, I might do some kind of like a random forest or something else. Spark has really good stuff for that. But I don't want to do random forest. I want to do a neural network classifier. So what I'm going to do here is I'm going to go ahead and I'm going to set up my, you see DL classifier, my deep learning classifier class here. This plugs straight into the Spark ML system, and I can go ahead and set all my parameters here. Then what I'm going to do, so I'm going to do that. Then I'm going to take my output as a data frame, and then so what I'm going to run here, and then I set this up, and you can see here I call my model.transform, and then I get my prediction data frame. My prediction data frame is going to have all of my outputs with a column which is going to have the prediction. So you can see here I have the data frame here, and I have my input column C1, 3, 2, C3, C4 plus the label. We have our feature vector, and then finally we have a prediction. It has what the model thinks the prediction should be. So then what I'm going to do is I'm going to evaluate my model. So in Spark ML, there's actually a lot of very sklearn similar. I know if any of you are familiar with scikit-learn, there's also very similar kind of model evaluation things. So here what I'm going to do is I'm going to look at the area under the precision recall curve, and I'm going to look at precision recall as metrics for my classification. And so you can see here that my precision and recall are, in this case, both 93%. My area under PRC is 1. So this is fairly good. And then you can see here I also have a confusion matrix, which is similar to what I showed you before. In fact, the overall function at the end is, I think, fairly similar to what we had in the last example. So that is it for Iris. So I have in the GitHub, I have some other examples here. I have, actually we have a number of examples that have been contributed by the Intel team. I've also done, there's a credit card default data set where we try to predict defaults based on there's also a fraud detection data set. There's also a number of natural language data sets that other people have contributed as well. And in addition, I want to actually introduce Alex. What he's going to do is he's going to, I'll let you guys ask a few questions before he comes up, but what he's going to do is he's going to show you how to use BigDL for a very common task, which is image classification. And so definitely something very relevant. And I think he's demonstrating MNIST, which is kind of like the hello world of image recognition applications, which is kind of the first thing that you're probably going to learn when you learn about image classification. So in the meantime, though, before we bring Alex up, is there any question? And I think what we're going to do also is after Alex is done, I think we'll both be around to kind of answer questions and demo some other things. So, but any questions? Yes.
So you mentioned that you're using it for NLP. There's an NLP library.
Well, so with Spark ML, we can use Word. The Spark actually has a very good Word2Vec encoder already, so we can go ahead and leverage that. Now, deep learning can be very effective at running that, at doing natural language, like say classification or clustering or other kinds of things. And then that's generally the approach that we're going to take, though. We're going to do our feature extraction using something like word to vec. There's other things we use like glove and other kind of word vector embedding as well for the feature extraction phase. And then what we can do, and one advantage of using Spark is there's a pretty rich, we can also use TF-IDF, or we can use topic modeling like LDA or other kinds of feature extraction in the area of natural language. And then what we can do is then, as we do that feature extraction, we can then build deep learning models with BigDL in order to do natural language tasks like classification or any other kind of natural language machine learning type of tasks that we may want to do. So
actually my question was about DLA.
LDA?
Yeah, BigDLA and topic modeling, if that has been done with BigDL already.
So there are several examples on natural language which are there. Now, as for LDA, that's something that is done. So that's something that is fairly that Spark ML itself has a pretty good implementation of LDA. So you might be familiar with GenSim in terms of its implementation of LDA. So Spark ML has kind of taken something similar to that and then implemented that. So what we can do is that I haven't personally worked on that problem, but I have worked on it with GenSim and Spark ML. So what we can do there is we can use LDA as a means of both dimensionality reduction as well as feature extraction from our natural language data, and then we can take our LDA data then, and we can use that as features of a deep learning model. So that.
So I know I'm asking too many questions, but like I'm using that as an example. Right? I mean, because even for sentiment analysis, you need a number of examples. Do you know how many examples do you need, and do they hand collect these before you get to BigDL? Because that tells you how sensitive it is to noise, right? As well.
Yeah, that's a really good question. I think that actually it's not really a question that's specific to BigDL. It's really just more, I think, kind of more focused, I think, generally on natural language data, right? And so, I mean, typically, like, a lot of times when we have natural language data, we have to do we call it annotation, usually in the case of natural language. So annotation is usually a big job, which requires a lot of human intervention. Usually, like for supervised machine learning tasks with natural language. So we talk about kind of hand annotation, and so that's usually what you call labeling in the context of NLP is hand annotation. So and usually, so you talk about building corpus or corpora of natural language, and typically we do annotation on that. Honestly, we can talk about that offline. How we do that with BigDL isn't really much different than other deep learning frameworks or even other machine learning frameworks, because most of that work is kind of done during the feature extraction and phase, which kind of happens before we really get BigDL in the mix. Once you've kind of extracted features and developed feature vectors, that's kind of when we bring in our deep learning models. Now that said, actually, we can often use deep learning models as feature extraction. Like for example, Glove and Word2Vec are actually both deep learning models that are just embedded and transform and embedded. So in that sense, we can then take our deep learning models and use them, kind of deploy them as kind of ways of extracting, features from machine learning. So it kind of goes in a loop that way. But yeah, I guess to answer your question, I think those things are definitely there, and I think that kind of doing machine learning on natural language again is something that I work with a lot, and we can use a lot. There's a lot of good tools for that. Like for example, GenSim has a lot of really good feature extraction, kind of things for natural language that you can look at. So yeah.
Thank you.
Yeah.
Can you embed this into the chip?
I'm sorry. Into what?
Can you embed this? What are the script we have? Can you put this into an embedded chip level or no?
Well, no, I know that probably what you're thinking, because I know that a lot of people are doing kind of custom ASICs and everything like that for deep learning, and that's really kind of exciting stuff. But what BigDL is actually focused on, it primarily is actually focused on trying to perform very well on kind of large clusters that already are doing data processing and machine learning. So it's not really focused on anything quite so exotic. I think though, that said, part of the virtue of this is that we can take BigDL right now and run it on our Hadoop and Spark cluster workloads and get really good results, without having to necessarily resort to TPUs and other things, which again are exciting, but probably not something that is going to be able to be deployable, tomorrow, right? So, yeah.
Thank you.
All right, let's bring Alex up, and he's going to talk MNIST and image recognition. So,
Okay. And while Alex is getting set up, I just want to thank you very much. Really enjoyed that presentation. And yeah, thank you very much. Okay. And yeah, while Alex is setting up, I just want to add a couple things that I thought of while we were listening to Tim. And that is that the idea of these models is really important. These models that you create are oftentimes transferable. Because when I talk about the models, what I mean is there's the script that you write that actually then uses the training data to then create a model, right? So the script is also oftentimes referred to as a model, but it's not really. The model is what gets generated when you run the script against the data, and that generates the model. And the model is what you then use to predict or classify or score or infer, whatever you want to call it. But that architecture is essentially what your script is generating and then running against the data. But once you've run that architecture against the data, you now have a model. Oftentimes that model can be reused. You can perhaps transfer it to either another framework like TensorFlow or Caffe or something like that, or you can also import models from TensorFlow or Caffe into BigDL and use them, okay? And so in that regards, I just want to point out that if you do have a model that's been created outside of BigDL, you can import that and use that inside of BigDL, which is very, very important, because sometimes if you want to use a model, you may not have enough of your own data. And so you can actually take an existing data set. For example, like ImageNet is a very popular repository of just photos of different things. And at the different layers of your model can be built up based on ImageNet, and then at the very end you transfer learn with your own set of images to actually complete the scoring or the classification with your data set. But it still benefits, your model can still benefit from all of the training it did on those other similar images or related images. So anyway, I just want to point that out, it's very important. Also up on the Intel Analytics GitHub page, there's actually what we call Model Zoo. Okay, so we started creating models that we then publish, so we've already done the training, and then now you can use those in your application as is. And so that may work for you, because maybe the problem you're trying to solve is similar to what we've already solved. Or you can use it, as I said before, for transfer learning, where you've taken that data set and you've now basically retrained the later stages of the architecture with your data set, and now it can use all of the previous learnings and add to its knowledge the data set you have, and now you have an improved data set that was, or a model that would be better than if you just trained it on your own data. So I just thought I'd share that with you. And there was, I think, was there a hand going up or a question? Yes.
No, I think I got it. But
Okay, Joe, you got it?
When I go to GitHub and I run this, take this down, and I want to say build my own models and data. Maybe
Well, if you're looking for the models, you can go to github.com/intel-analytics. And then I think there's a BigDL repo. And in there, do a search for Model Zoo. And if you can't find it, then let me talk to you later and I'll help you find it. And then you had a question?
Yeah, so these models can be taken and improved upon, because you mentioned as if you take the data set and you start with that, but I won't take your model and improve that.
it's called
Right.
transfer learning.
Yeah.
So yeah,
That's,
Yeah, and basically the way it works is you have all these weights that have been put into the model, and those weights are what are actually used to do the inferring or the scoring, and then
just the weights.
you can remove like the last layer of weights and then retrain it with your data set, and so then that last layer actually points to your classifications versus the classifications that were already there. I'm simplifying this, but that's essentially how it works. And it's a little bit complicated, but it can make the difference between workable and not workable if you're using, if you don't have that much data. So I just want to point that out because it's very important that you know that BigDL can work with all these other data sets that are being created out in the wild or wherever. So, and all right, so with that, I want to introduce Alex for some reason.
I'm good.
Oh, you're good.
I'll turn it off.
Okay,
So
nice.
we can blast you.
So I'll turn over to Alex, and then I'm going to have to take off. I'm going to go coach my daughter's soccer team, so I'm going to be leaving. I'll leave you in good hands. And
I heard that talk 4 times, so
Yeah.
forgive him.
Yeah, so we'll turn over to you. Okay,
Thank you
thanks
so much,
All
Dave.
right. Thank you, everyone.
So we're gonna have a few more images and a little bit less text in this presentation. So hopefully together you want me to overload it. So my name is Alex Kalanian. I work, I started working in machine learning late 90s back in school, where I was actually working on computer recognition, image recognition. And at that time it was a lot of fun, but the hardware was pretty weak, not powerful. I remember optimizing our software for my thesis to take advantage of the entire 64 megabytes of memory available to us at the time, which was quite exciting, and I sped it up by 4 times, but of course we could only do the simplest tasks on very small images. So then I worked on various data-intensive applications, first at Yahoo on a pretty large scale doing user acquisition. Then more recently, I worked with a startup called Home AI, which exposed me to the entire stack of machine learning, from classical machine learning algorithms to image recognition, facial recognition. That's where my interest in image recognition was reignited from years ago to recently. And recently I joined a company called Seismic. Seismic is a very interesting company. It's an AI-powered marketing company. It has multiple products for site optimization and for user acquisition and for targeted advertisements. So basically it helps advertisers to reach the right audience. And we use the machine learning on some of the largest scales that you could find outside very large companies. So to give you an example of the things that we work on, we process that many requests per day, which is not a typo. If you will scale it to a bit smaller time periods, you'll get about 1.2 million per second. So yet it's not a widely known company. Hopefully it will change soon, but again, we work on really challenging projects. So that's the inference part. So that's what we execute in real time. To train these models, we have several petabytes, number of petabytes of training data that we have to train. So we have to use very large Spark clusters to run these data sets, be very smart about how we use algorithms. And so hence my interest is now in the joint applying image recognition, something that I like, to Spark and BigDL library, which is the only really library available on Spark natively. A little bit of initiative stuff. Here I'm copying Tim. So later I'll show you a workshop piece. You might want to take a picture of that. This GitHub will give you instructions how to get the Docker image and install on your computers after this session. Please do not download the Docker image right now. It won't work. The connection is way too slow.
Works just great.
It does?
Yeah.
It's 4 megabits per second.
Well, like you said, things are faster now.
All right, then maybe I'm wrong. So, everybody took the picture of this?
No, just a second. I'm slow, however.
3, 2, 1, 0, -1, -2.
Thank you.
All right. So, how many of you do data science, any kind of machine learning algorithms? So, who knows what logistic regression is? A few people. Okay. So, I'd like to show you real quickly a difference. I think it's a very important difference between machine learning and deep learning. So, there's a site called TensorFlow Playground, which would mostly be around neural networks. But what I did here, I just created a pseudo-neural network with a single neuron. If you look at the math, then it ends up being exactly a logistic regression. So what it will do logistic regression of data set. So now what the logistic regression does, it tries to separate the data points by using a line. You use a linear combination.
So how's that different from linear regression?
So linear regression does a regression. It gives you basically a continuous variable, so you predict between 0 and infinity. Logistic regression converts the output of a linear regression into 0 and 1. You're absolutely right. It's linear regression, and on top of it, there's a nonlinear function, usually a sigmoid function, that basically squeezes all the outputs between minus infinity to plus infinity into 0 to 1. And 0 would be either negative response or 1 class, positive would be 1. So in this case, we want to have a boundary between these data sets so that when so this is our training set. So if I have this training set and I said, I want to use logistic regression, what do you think will happen? Well, it's gonna draw a line, right? Say, well, I'll separate it. You got this on the left, this on the right. So now when I do inference, I take a new data point, x and y, right? That's what I pass in. It will be somewhere here, for example. I pass it from my model now, and it'll tell me it's blue, or it's 1.
Oh,
And I'm very happy, right? So this model worked really well. I was able to do that. So how about this data set? If I apply a logistic regression to this data set, what will happen?
Depends if you.
Well, we'll try to stick in a line somewhere, right? So, and it will, it will be forced to stick a line somewhere. It can't say no to us, but it's not going to make a lot of sense. So it's going to minimize this loss function, but it's really not doing anything useful. The loss function is still pretty high and not really good. So should we give up now? No? What should we do?
Put a kernel on it.
So you can go for a polynomial regression.
So now we can do a feature engineering. So now you're hiring a very expensive data scientist. They come in here, look at this data and say, hey, there's your problem. You're trying to stick in the line, but it should be more like a circle, which is polynomial features. So here I have them. So I'm going to change my inputs. I'm simply going to square my x's and pass now squares to the same logistic regression. So what will happen now? Boom, a circle. Great, so now we're happy, I go home, you pay me really well, excellent. Everybody's happy, right? Let's do another example. So let's say this one, and I'm gonna go back to, again, this one actually. This one looks pretty scary, right? It's like kind of worse. Again, a line isn't gonna do anything, it's gonna be can't even decide where to put it, somewhere here, right? So what should we do now?
Cluster.
Well, here actually, it's still feature engineering, and that's a bit more complex. So actually, x1, x2 is the answer. So if we do this, it actually will separate them quite nicely. So basically, as a data scientist, you have to know all these things, and these are very contrived, simplistic data sets, right? They're very obvious what should be the answer most of the time. Even here, it's not entirely obvious. But now imagine you're throwing like a terabytes or petabytes of data that you need to sift through. You can't even, it's multidimensional. You can't even look at it nicely. You can in a simplified way. You're trying to make sense out of it. So you basically do lots of experimentation, and it just takes 99.9% of your time. It runs forever until you figure out what features to stick into this logistic regression, or pretty much any of the random forest. They will behave in exactly the same way. If you give them the wrong features, you're not going to get a good result. So deep learning, what's the difference? So now what I'm going to do, I'm going to design a network which will have 3 or 4 layers, and I'm just going to randomly add some neurons. I think this should be enough. And I'm going back to my raw inputs, x and y, right? This is what I get for free. X and y, people throw at me this data and say, do something with it. And let's start with, the more difficult one. So I've done 0 feature engineering. I just shoveled my initial data into this network, and it was able to figure out, what it's supposed to do. Let's try this one. Well, this one will be very easy. It will do it instantly. Again, 0 feature engineering. What about this one? Actually, not quite sure if it will be able to figure it out. Well, look. So that's the key difference between deep learning and not deep learning. Not deep learning, you will be doing feature engineering for the rest of your life. Deep learning, the promise of it is that if you build it, and again, the network needs to be deep enough. If I'm going to kill a few layers and try to get away with this, actually I still have 2 layers. If I'll do just one, the data set is simple enough. So even 1 layer, but with multiple neurons, give me enough flexibility to fit that. Now, I won't be able to fit this one, though. This one will be pretty tough to fit with so few layers. But if we simply add more layers, right, that's how we solve the problem. Not a feature engineering, but saying, hey, more layers, more layers.
Well, if you ultimately add as many pixels as you have in the picture, you solve the problem pretty simply.
Well, but then you have overfitting, so you have to
Which
test
is what
them.
you had before, since you were able to go on and drop all those other layers off and still get the same answer, right?
Yeah, so basically I had redundant layers in the previous example, so I went too deep too early, so you can scale it back. But, well, this will take a while for it to kind of make sense out of this, but eventually it will figure out kind of a spiralish structure. So yeah, I gave it
4 layers, you don't need 4 layers for a circle. I just wanted to give an idea that once you have a network and it's deep enough, and you have enough data to not overfit, you're gonna fit any input shape. So the idea is the network is doing a feature engineering for you, which is kind of what it's designed to do. Now, this doesn't come for free. So the downsides are overfitting, which happens all the time with neural networks, and it requires you to have a lot of data. So to train a network in the real world, you need a lot more data than you need to train a machine learning algorithm. Like a lot more could mean 100x, 1000x, 10,000x, like a lot more data.
For the deep learning?
Yes, but if you have that much data, you can throw that data into a system, then you can use deep learning, which is what we're gonna do with images, which is kind of one thing where we do have a lot of data are our images, right? Because at this point, we have tens of millions of labeled images in different data sets. And we don't really know how to classify images. We don't know what features should be. So that's where deep learning kind of shines. And same with natural language processing, right? There are some algorithms that don't use deep learning, but really at this point, all of them rely on deep learning in one way or another. You have a question?
Yeah, but I'm kind of new at this, so I don't know if it's going to make sense. Okay, yeah, you've got an image, so you've got two-dimensional data. I deal with things that have more than 2 dimensions, perhaps.
Oh,
Look
yeah,
at- Does that make your analysis a lot, do you need a lot less data if you can get that? Maybe if you're looking at someone natural language processing, but you're listening to intonation as a third dimension aspect to it.
The great question, and the answer is a few slides later.
Oh, sorry.
So, no problem, no, it's an excellent question. I like when people ask the questions that I have an answer a couple of slides later. So, Tim talked about neural networks, and he used a classifier network to classify, if you use the classification task, and what he used is a feed-forward network. So if you do any research on the internet on neural networks, you'll see something similar to this picture, and on this projection, all the colors are exactly the same. That's not good, I need to redesign that. I actually have different colors, but it's like color-blind projector. So to me, it's not very meaningful what this means, so I usually like to break things down a little bit so they're more intuitive. So I'll show you what actually is behind this. And behind this, when you do the pass through a neural network, is actually a very, very simple thing. And that is we essentially apply a simple formula, which is this linear combination of our inputs, right, and weights, which doesn't matter where they came from right now, but basically we have weights for every single combination. We apply this formula, and we get the result. So that's the first step. Now, by itself, that wouldn't be enough, because if we just use linear combination of inputs, it turns out we can't do anything interesting. It's just going to be a linear function, and we know the linear function isn't going to do anything. So we have to apply nonlinearity, a nonlinear function on top of that. So there are various nonlinear functions available to us. The most popular in deep learning is rectified linear unit. Its most popular is because it's very easy to calculate, it's really fast, and we want these calculations to be very fast because we're going to apply them millions and billions of times for big networks, right? And the way rectified linear unit works is if the value we pass to it is negative, it's going to truncate it at 0. And if it's positive, it's going to pass it as is. So it's a kind of strange, simple function, but it actually has great features that we want and easy to calculate. So in this case, this would be 0. Then the next calculation, so again, we have now a different set of weights. We have our linear combination. The number is positive, so it's going to stay as is. The third number is actually negative. I need to move it by a little bit, so it will become 0. And the final number is positive, so it will stay as is. And that's pretty much what the network does. It just applies this formula again and again and again. There is really nothing complicated going on at each step. But because we have so many steps and they learn from each other, that's how we get this complex behavior. Another important feature of neural networks is that they see layers see only one level before and one level forward. So they don't know what happened before. It's completely, it's unknown to them. So they only rely on the inputs from this layer. We could have had 20 layers before this layer, and this layer will not know that. That's a very useful feature. We'll see how it helps us in the future. So now we use only these layers inputs, and we calculate outputs. There'll be 0, there'll be positive. So we get some outputs that don't make much sense to us right now. They'll make a little bit more later. But that's basically how the forward pass works. So if we take a network that's big enough, we can pass almost any data and train it to learn anything. So in this case, we can take a big, fully connected neural network and pass, and that's what it is, and pass an image. And hope that we can train so it will learn to recognize images, and we're done, right? So that would be pretty exciting and pretty simple to do. So this number 4 looks to us from this MNIST dataset like this. In reality, it's actually a matrix of numbers. So it's a two-dimensional matrix. You can kind of make out number 4 here. 0 means we have black intensity completely, and non-zeros is some kind of white or grayscale. Now that's a very simple image. Most of the time you're going to have some background there that has all kinds of things in it, and it's a pure black background, so it's a pretty simple data set, but that will help us understand a couple of important features. So if we do that, let's see what happens. So what I did, here's your question. The neural network is a linear thing, right? What happens if you do two-dimensional? It doesn't really matter. We basically take the linear array and just fold it in layers. So it's absolutely, it's just meta representation, right? So you can draw 2 long lines and connections, or as I did here to match more our input, I just said first 3 cells, second 3 cells, the other 3 cells, and so on and so forth. And that's your square input. So same thing. So linear, or just, you represent as a square or a rectangle, it's exactly the same thing. So, as you saw from a few slides ago, this is the input, let's say this is the image, and this is the next layer. The way we calculate each value of the next layer is we take all the values in the previous layer, right? Apply weights, sum them up, and apply the nonlinear function. And so after we do that, we have our value 1. We're going to write it here, whatever that is. Then we do the second cell. What are we going to do? Well, same thing, right? We're just going to take all the input values, use a different set of weights. So all these weights are different from each other. We don't know what they are, it doesn't really matter right now. And we calculate the second value, and then the third value, and the fourth. So that all sounds great. It kind of matches exactly what the fully connected network does, only now we're applying it to images. So in theory, it should work. But let's do some quick math here. So let's say we pass an image that's 200 by 200 pixels. It's not a huge image by any stretch of imagination, right? It's like a smallish image. So how many total pixels are we going to have? How many values?
40,000.
40,000. Okay. So to calculate the first value, we need to take 40,000 input values, apply 40,000 weights to them, we get the first value. So to calculate all the values, how many total number of weights are we going to have?
So 40,000 times 40,000.
40,000 by 40,000. Who is good with zeros? How many zeros would that be? That'd be lots of zeros. It would be 1.6 billion connections, right? So now we took a very small image, and it turns out that in order to do anything with it using a fully connected network, in just the first layer, we're going to have 1.6 billion parameters. Each parameter, let's call it a 32-bit, floating point, single precision. It's 4 bytes. That's 4 gig of RAM to just hold the first layer. And we know that a single layer rarely does complex things, so we want more layers. And if we throw in 10 layers, which is not an insane amount for a computer vision type network, you get 16 billion parameters. So there are 2 problems with this. Problem number 1 is that it's just hard to compute, right? First of all, there's not even hardware out there outside some supercomputers that's capable of doing that, holding all that in memory. 2, because there are so many values, and remember, each time we pass the image, we have to repeat that calculation for every single value. We'll be doing, 16 billion, some multiple that operations for every single image, right? So that will be taking a lot of time. So if you have 1 million images that you want to pass through the system, this will take forever. So computation is not feasible even today, even with GPUs, even with everything. But there's a bigger problem here that's more fundamental, and that is, to train this network, we now have 16 billion variables that we have to train, right? There's so many of them. And there is a rule of thumb, and you can do the math in kind of different places will give you a different answer, but in my mind, if you want to train that many independent variables, you gotta have at least sort of in the same ballpark as many training examples, right? So here we're talking about billions of labeled images that we're gonna have to pass through the system. So the system is very slow, and we have to pass lots of billions and billions of images to try to train it. Well, first of all, there are not even that many images even today out there. The largest labeled data set is ImageNet and has about 10 million images, which is almost like 1,000 times fewer than we would need for this. And of course, the time, even if we had those images, the time it will take to train this network would be measured in many years. But you're welcome to try. It's a very simple design. You can implement in TensorFlow, BigDL anytime, and please come back when you have first results. Now, what we're going to do, we're going to actually kind of leverage ideas from a fully connected neural network, but redesign it slightly, so it's not as bad and actually does what we want. And that goes back to work by computer scientists like Jan LeCun, who designed the most well-known network back in 1998 called LeNet. But he actually relied on the research done 30 years earlier by two neuroscientists, Thorsten Hubel and David Wiesel. And what they did, they took cats, anesthetized them, connected to their neurons, and then started showing the cats different objects on the screen, on a very old CRT TV. There are videos on YouTube that I recommend you do find in your free time and look up, because they're very fascinating. And at first, their experiments didn't work at all. So they were showing some dots, they were showing some pixels, and neurons would not fire. There would be like nothing going on. Until, by pure accident, they were sliding this dot written on a piece of glass, because it's 1963, right? There are no computers yet, into the field of view of the cat, and the edge of a glass triggered a neuron. And so they found that the neuron that they plugged into would respond to extremely precise type of image, and that is the vertical line under this angle that's being moved left to right. That's it. If you move it in a different direction or it's a different angle, it would not fire, which was quite bizarre, right? So, especially since neurons are all the same. We, or cats, don't have neurons that are designed to recognize these weird lines. We don't have different neurons that recognize chairs. They're all the same. And so they kept doing these experiments for a few years, for which they got a Nobel Prize, fortunately, because the work is has such huge impact. And they figured out that the visual cortex has the layered structure. So there's a first layer of neurons that responds to very basic things. There is a light, there is no light, there is a dot, there is no dot. So eventually they found those neurons that were responding to those simple dots. Then the next layer uses those inputs and starts looking for more complex things like lines, angled lines. And higher layers look at more and more complexity, moving lines, moving circles, crossed lines, and so on, until many, many layers later, could be hundreds of layers, the cat's neurons respond to objects like mice, like dogs, things like that. Very high level behavior, right? That's built upon the more simple concepts. So, Jan LeCun took these ideas and used them in a neural network. And the neural network will want is sort of this kind of simple behavior. We already have the hierarchical structure. That's where it's important. As I mentioned, the neural network only looks one layer back. So whatever you give it, it bases the next layer on top of that. And we hope that we'll build a network where early layers will recognize simple things, and as we go higher and higher and higher, they will learn to recognize more complex things until we'll have these output cells that will tell us that's a giraffe. This is, a red car. To achieve that, and we know that the fully connected network will not work because too many parameters, we can never train it, it's just not good. So two key features that still leverage the fully connected network design, but make it very different, are convolution and pooling. And so once we have those two, we can build a convolutional neural network. So what is a convolution? If you remember, in the fully connected network, we take all the inputs, we calculate the sum, apply the function, and that becomes our first output. So we take into account absolutely every single value of the entire image. What Thorsten Hubel found is that actually cat's neurons, the ones in the very, very front layer, they do not respond to all pixels on the image, but they actually look at the very small area. So one neuron will only fire when there are things in this area. Once you move out, it stops responding. But a different neuron will pick it up and will start firing. And so that's the concept that goes into design of convolution. What convolution is basically we say, we're not going to look at the entire input field. Instead, we're going to look at the small section, in this case 2 by 2, and apply weights to it like we did in the fully connected layer and calculate the output. And that's our output. In fact, we're going to use the same weights and we're going to shift by 1 and calculate the second output using the same small number of weights. And we're just going to slide this kind of field of view and we're going to calculate outputs using only a small input fraction. And this will only give us 4 weights, well, in this particular case. So we went from, in this case, from 15 by 15 to 25 weights to only 4. And also now, in reality, of course, that's a bit too few. I didn't want to draw too many lines. In reality, we'll see in a neural network, a typical size of this connection is about 5 to 5 or 7 to 7. It still gives us a very, very small number of weights. A lot less than 16 billion as we had in the fully connected version. And also, yeah. So, and if you look at it, again, if you do research, read up on the convolutional neural networks, people will often use a term a filter. So that's essentially what it is. The weights that we use here, they simply represent as a matrix like this. And you can imagine this matrix sliding over the image. And because our weights are fixed, they no longer depend on the image size. If your image doubles in size, we still have only 4 weights to train, which is a small number of weights. And here's an example of manually designed filters. So for example, a vertical filter would have all zeros and ones in the middle. So if we apply it to an image, it will start emphasizing vertical lines and kind of squashing everything else. And so this image will go to the next layer. So the next layer will see an image with vertical lines, if there are any. But if there are not any, it will not see any vertical lines. So the next layer will start paying attention to vertical lines and kind of thinking, okay, if there are vertical lines, it's probably a house. If there are no vertical lines, that's probably a lake. Eventually it will get to that level. Horizontal filter, same thing, only emphasizes horizontal lines. So that, of course, you can easily design it. The formula is very simple. You can write this code in Python, 10 lines and run it. The question that I have is, where do these values come from in the real neural network? Who specifies them? How do we know what filters should there be? Any guesses?
Well, the system should be able to figure it out.
How would it figure, like what? Was that?
You talk about graffiti?
Was that?
Intentional life or the weight?
No, I'm saying like, so I have a neural network. So neural network is basically a series of layers which are a series of weights. First of all, when I create from scratch, what would those weights be?
Uninitialized.
Initialized, right? Like, well, it could be zeros. The 0 is not a good number, but let's say
Random.
it's random is better because it actually trains. Actually, zeros are pretty bad numbers because the network might not train at all. But let's say they're 0, so we don't know what they're supposed to be. But we know that 0 is not going to do anything for us. So how do we?
Well, you
train it. Yes,
that's
yes,
right. So you
exactly.
have to have supervised data.
Exactly.
Showing what you're looking, what you're not. That goes on the out, that goes on the in, and then you train it going.
So yeah, this filter is humanly designed to illustrate these things, but in reality, in neural network, these filters are just weights. Initially, they're all random, but then we train the network, and the trained network figures out based on the.
So this was discovered. This was not input. I mean, it turns out the network figures it out.
Well, was not. This is a contrived example to show what the filter does, but it's quite possible that given a certain training set, a neural network will figure out to use this filter. Maybe not as precisely as a line, maybe you have like some smallish numbers here, but it will do it. In reality, neural network can learn pretty complex filters that might not make a lot of sense to us. That's a known problem with deep learning. If we look at the numbers, the weights, they kind of don't really match anything. There is no magical number that says, I'm looking for a nose. It's just a bunch of numbers, but once applied, they lead to the result that we expect, the right classification. So that's the one key feature, and that's a convolution that is applied to a small field of view and just does the one-step adjustment to an image, and then it goes up. The second feature is pooling, which is basically scaling. So if you take an image, you put it in Photoshop, you say reduce the size by 2, it will apply some smart algorithm to make the smaller image by kind of preserving the features. So the algorithm is pretty complex. We use a much simpler algorithm in neural networks because remember, we want things to be very, very fast. But turns out, for the purposes of the neural network, this works just great. So the way we scale it, we take 2x2 field and we pick the max number. This is called max pooling. The alternative is average pooling, where it takes the average, and the average is slower to compute because you have to do some additions and divisions, and it turns out that max pooling does just fine. So we took this image and we shrank it to a much smaller size. And the reason to do that is that in the convolution layer, we picked up some features which are important in the picture because they're there. So our filters extracted them. And now we take these features and we shrink the image, preserving only the most important features. Because we don't want to deal with large images at the end of a network. We want to start reducing its size. So eventually we should end up with just a few outputs that tell us what class it is, right? So we keep shrinking things. So if you look, well, my top is like colors completely invisible, so we can ignore them, look at the bottom. And once we have these convolution and pooling layers, we simply stack them on top of each other. And we can go as deep and as far as we want, or as our data set allows. So for LeNet 5 architecture, it's 2 layers repeated of convolution pooling. And remember, pooling shrinks things. Convolution again creates new derivatives, and we shrink them even further. And finally, by here, we have pretty small images. And that's where we can use a fully connected layer to do classification. Because we cannot apply a fully connected layer to the original image because it would be too huge. But once we're small enough, then we have a fully connected layer and we have our outputs. So this is for object classification. But we're going to look at LeNet. That is usually applied to digit recognition, handwritten digits. And the way we classify them is that we have this output array with zeros and only hopefully one 1 in there that will tell us which number the network thinks it is. So in this case, number 4. So that would be kind of our well-working, well-designed network. Well shared, yes, questions?
Isn't the weight of the configuration in the first stages when they're scrolling across the screen, the weight automatically adjusted was based on the content?
So weights never change here. Now the output will change based on the content, right?
One thing you haven't talked about is the threshold. I don't believe you haven't talked about the threshold function that comes out potentially between these layers, I guess.
It's the same function that's rectified linear unit.
Okay.
So if you think about it, that's why I have this first slide. So this is what we had in the fully connected. So we multiply weights, we sum it up, and we apply the rectified linear unit, which truncates if below 0 or passes if it's positive.
That was my only point.
That stays as is. The only difference between a convolution and a fully connected layer is that instead of looking at the entire input space, we say I'm looking at 4 in this case. And in fact, instead of having different weights all the time, I'm going to have the same set of weights, and I'm going to apply them to the entire image. So it might not be obvious from this presentation. I keep working on this, studying more kind of illustrations for things. But having this type of approach, same fixed weights, has another incredible property, is that it allows to detect an object regardless where it's in the image. So if you think about it intuitively, if you have fully connected, once you learn that, the dog in this corner looks like this, once you move the dog here, you lost this knowledge because the weights that pulled the data from that corner are completely different, so the network will be helpless. So you really have to give an image with a dog in every single place for the image to be, for the neural network to be able to find the dog. But if you use a convolution, once it learns that there's a dog here, it's going to find him anywhere in the image. So it's not entirely obvious, but if you kind of think about how the weights work, that's an incredible property because that's what we want. It's called location invariant. So, as you can see, the convolutional neural network is just like regular neural network. It just does a couple of adjustments and introduces the concept of pooling to shrink the size. And in fact, at the end, we have a proper fully connected layer. And that's how we can solve all this complex computer vision problems. So I'll show you. Do we have time to see the code? Do you guys want to, what do you want to do? So I have instances in Amazon right now working. I can send you links. You can try to touch it with your hands. Would you like to try? Okay. You'll do it afterwards? You want to
see where we are. Yeah.
Okay. Okay, so here's what I'd like you to do. Let's start with Tim to be as a test test person.
How many cats did he have to go through to get this Nobel Prize?
I really did not look into that, and I was hoping that no cats suffered in a way. They were sedated, but there are great videos on YouTube. I would show if I had more time. I see what's going on. Okay, can you pick the first URL, Tim? Yeah. So, what's your name?
Bill?
Bill. Can you try the second one? So you see where this is going, right?
Yeah.
Well, we kind of run the wrong direction. So it's, sorry. Make it better? Ooh, wait.
That helps.
That's what I want. I'm going to bring the displays into mirror mode so it's less insane. Okay.
Not so sure.
All right. Even better. Okay, so Bill, you got this one. Try 8004, 8005,
I get a,
8006.
It gives a security warning, but just so.
Yeah, it gives security warning because of cell signs. Actually, the search should be legit, but I think it's expired. I use Let's Encrypt, which is every 90 days, and I don't do it automatically. So, but if you say I'm fine with it, I accept this virus voluntarily, it'll let you in. So, who has 6? You got 5, 6. So I'll just gonna. We have enough. So 7, 8. 8. Will be 9. If you want to do this. 10, 11. You're not gonna do. Okay. 9. So we run. So there is a second one. The second batch 2 with the same number of numbers. So you kind of see where this is going, right? I think we just need a couple more. So.
are we becoming neurons or?
Yeah. So what you should see. Actually, let me see what I can use another one. What you should see is something like this. If you see it, go to notebooks. So who does not see it? Who is trying to connect but does not see this?
Structure, 2017. Structure, 2017 password.
What?
800 or 8007?
8. Everything starts with 8. 006, 007. You're in, right? And the reason why there are different URLs is that I have 3 instances running 10 Dockers side by side. So the instance is loaded. And so if we're out of one block, we go to another block. So if you pick one of these, you should get to it. If 2 of you pick the same one, you'll be able to see how other person tinkers with your notebook, which also could be fun. All right, did you get here? You see something like this? Great. So you go to notebooks, ignore everything else because it's a Spark and BigDL setup. So this is all in Docker container. If you took the screenshot or the picture, and we'll share this presentation with you on my GitHub, you go there, it'll give you steps how to download Docker locally. You can put it on AWS if you want to. You can even install things manually. So you can do any of these things. So yes, if you are here,
Click it, the first one.
yeah, so you can click any one because you're all going to get different Dockers, so you're fine. Okay, are you here? That's a Python notebook running BigDL. It's very similar to what Tim talked about. So you can execute cells by doing Shift-Enter if you don't want to do it using the mouse, because I do it a lot and I don't want to use the mouse for that. So the first part imports everything. This cell, SC, simply lets you check that your Spark runs properly. Once my first cell completes, I'll get to it. So now it shows the start, means it's running. Once it's done, yeah, there you go. So if you say SC, you should see this. You should see Spark context. It means you're good. If you don't see that, it's an empty string that something is broken. Hopefully you don't see that. You need engine, initializes BigDL library. So MNIST Dataset is I'll print some images in a moment, but it's a set of images that has been designed a long time ago and used for many different algorithms as a measure. Basically, it's the same data set that people used a lot and still use to try different algorithms so they can compare results. So to compare results of different algorithms, you have to make sure you use the same data. Otherwise, they become impossible to compare. So this data set comes with two parts. One part is a training set, which has 60,000 images, 28 by 28 pixels, not too huge, and has 60,000 labels that says what those numbers actually are. And then there's a second set with 10,000 images, also is coming with labels. But the idea is we'll use the first 60,000 to train the network, and then we'll use the 10,000, pass through the network without telling the network what the label should be, get its predictions, and then compare them. And then we'll know the network said versus what we expect. We'll be able to calculate our accuracy. Hopefully it's very close to 100%. It's never going to be 100%, but there. If it's low, it means we're doing pretty poorly.
So you have to do each step? You have to do shift enter on each step?
For each image, oh, shift enter, yeah. If you
Yes.
want to execute the cell, you do shift enter. It's one cell at a time, yeah.
Each of them?
Yeah. So you're kind of executing lines one by one. You can run the whole thing at once. And once you know what it does, you simply want the result, that's what you'll do. But right now we're going one step at a time so I can show you what actually is happening. So this function actually takes the training set and just prints a random image. And I'm going to now shrink a little bit so it fits here. And it shows the label that actually came with it. It's number 8. You can see what the matrix looks like. It's kind of 8, and you see that the actual image. So that's what we have as an input. We have an input is this thingy and a label that says that's 8. That's a labeled data set. And all, that's, am I using a random number? I think so. No, I'm using actual fixed number. So you can put any number here. You'll see number 1, or check number 0, index 1, other index, number 2, and so on. 60,000 images like this, right? So that's about 6,000. It should be exactly 6,000 of each. So there are 10 of them. Here I'm just going to check how many classes we have, so how many different labels on the training side. It should be much faster, but we'll see what's taking it. So who got this done? I don't know why it's thinking so long. It should be pretty fast. Okay, so what number do you have there?
I got 8.
You had 8?
Unique train tables, a class count?
Class count, yeah.
Oh, okay. Let me class count.
This notebook could be,
Class count 10.
yeah, that's exactly what we would expect, right?
Yes.
Might try a different notebook. So we have 10 different images. That's a good way to make sure our data is good, so nothing if it's going on. So I'm going to switch to a different notebook, to a different instance. I'm going to start it.
Are we running this, we're running this on your machine, right?
You're running this on the cloud instances.
Got it.
So it's a pretty potent machines. They should all be done pretty much instantly. Yeah, this all runs on my machine. There you go. Okay, so we're out. So 10 classes, and if we do say training label show me unique, NP unique, you'll basically get what we expect, 0 through 9. So far, so good. Data normalization. So as I mentioned in the very first example, is that we do not do feature engineering with deep learning, right? In this case, we're going to take images and just throw them at the network as is. Whatever numbers are there, it'll have to take them and learn something from it. There's only one adjustment we're going to do, which is normalization. And in some cases, you don't even have to do it for bigger networks. And that is basically a shift from 0 to 255 to the 0.1 to 0.9 range. It's just basically we're going to scale our numbers. And that will make training slightly faster and better. So it's okay not to do it, but for this example, I'd like to do it because it makes things easier. So nothing really changes. It's a simple arithmetics. There is nothing complicated going on. So black color will become 0.1, white color becomes 0.9, and everything else will be in between. So we'll do this normalization, run it. So now I have 2 data sets, normalized training set and normalized test set. And this is our network. That's pretty much what it takes to build it in BigDL. And it follows, well, you don't have that slide right here, but if you look at the slide of the LeNet design, pretty much 1-to-1 correspondence, right? Convolution, nonlinear function, max pooling, and here the convolution is 5 by 5, as I mentioned, typical size, 2 by 2. Pooling, convolution again, 5 by 5, nonlinear function, max pooling. Reshape, it simply internally changes the layout of the data, so we now go from a square laid out arrays to like linear arrays. It really doesn't change anything else. And now we add 2 fully connected layers on top of that. I have one more commented out here. So all this is basically subject to testing how your network works on your data set. And you can add one more layer, you can remove it. And you need to look at the training data versus test data to see, you know, if you want more layers or not. So I have a question for you. So if you, let's say you train any algorithm, maybe even this one, and you get training accuracy 99%, but you get test accuracy 70%, what does it mean?
It's not biased, but I mean, the training certain test set must be biased towards specific classes.
That's possible, but let's say they are all equal. So you train, you get a really high training accuracy, 99%. You do test accuracy, 70%. Well, you know the answer, I wasn't asking you. So yeah, so that's so-called overfitting. And what it basically does is the network really kind of adjusted for the, if you think about it, if you have like a function that goes like this, and we have dots on it, we can also draw a function that goes like this and goes through every single dot. So in the training set, it will be a perfect match. It covered every single point. But of course, that's not what the function is. So when we're making a prediction, it will be completely out of whack. So that's why you get training accuracy really cool, really good, really high, but your test accuracy says it's a bad result. So the point is when the network becomes too big, it starts overfitting. So you get high accuracy on the training, but low accuracy on the test. So let's create this model. 3 epochs is how many full iterations we're going to do. The more the better, it's going to be converging, so after 10, 15 it should be good, but we're not going to wait that long. Optimizer. So now we have the network, and the network is comprised of the structure. It basically says which layers follow what, right? An initial set of weights, which are random. So by itself, this network is kind of useless to us right now. We need to train it. And in BigDL, the thing that trains the network is an object called optimizer. And here we specify a number of parameters. One, we say what we're going to train it on. Well, we have a training set. That's good. And then we're going to say which criteria we're going to use. This is so-called cross-entropy criteria. It's a formula that basically calculates how close our prediction is among those 10 classes. So the worse our prediction, the higher this value, so the network knows that we are wrong. And when the values match, it will be 0. And there's already, usually going to be, for all classifications, we'll be using this one, pretty much always. Very rarely use something else. And the optimization method is how exactly we're going to train a network. And all the methods are typically derivatives from so-called gradient descent. So you probably heard that. If not, you will hear a lot more. And in this case, we use stochastic gradient descent with certain parameters. There are 3 or 4 different methods. Other methods, they're also very similar to each other, but have subtle differences. For this particular example, it doesn't really matter which one you use. For bigger networks, it might become important. So once we have the optimizer, we'll also say the validation. Validation does, remember, when we train, our training accuracy will be increasing. But we also we're going to keep an eye on our test accuracy, see if we're overfitting or if we're doing well. So at every step, we're going to run our network through the validation for the test set and see how we did, because that's our ultimate test. And these are basically where we're going to write the output. And once we write this output during training, then we can use TensorBoard to observe how that's actually working. So let's start training. Well, that's not very exciting. So it'll train, it'll take a while. So in Tim's example, for his small classifier, it took 10 seconds to train. This will take a couple of minutes to train because we have a lot more images, that's more data. Our network is bigger, and more parameters to run, so you can see how this takes time, even for small things. In the meantime, we can look at what's going on. So if you take this URL, we'll remove, you say, basically you start with what you have and replace, instead of HTTPS, do HTTP. It's important, just TensorBoard does run this SSL, and replace 8 with 6. So it's the same URL you used, only you just make it non-SSL and use different port. It should show you this. That's a TensorBoard that's right now showing how my training is going. And what you see here is the loss function. The actual value doesn't really matter. What matters is it's declining. So it's good. Our training is going in the right direction. And once we trained for long enough, we should be able to get the accuracy. There you go. And then just by probably just out of luck, I get the accuracy that's already very, very high. So it's 86%. You could see different results because your results may vary and probably will vary quite a bit. So I'm still training and I'm here. Do you see this page? Did you get to it? No? So you take the same URL you had here, and normally instead of HTTP, you do HTTPS, you do HTTP, and instead of 8, you do 6. 2 changes. And it should give you your tensor board that matches your notebook. If you go to someone else's tensor board, if you put something, some other number, then you'll see their result. Did you get to it? Okay, so yeah, so this now, it came to its senses. So I started at 86%, and now it's increasing, 92%. My training loss declining, so when we're finally done, we'll see what the final accuracy is. We're still training.
What's the lighter line?
I'm actually not sure. There's some other, I suspect that maybe somebody is running the same notebook on me. Yes. Or it's just an artifact of represent because it doesn't really do anything here. It doesn't show me. So this blue line, see when I mouse over, it gives him my. Well, I need to reload this. So it's quite possible that BigDL writes some some output that's not.
And this is all running on this Intel machine, is that correct?
Yeah, 100%. This is all CPU. There is no GPU at all. And the value of this, so when
Spark?
Yeah.
Okay.
So there's a, so it's, okay, I'm done. So I trained took 2.5 minutes to train. And my top accuracy right now is 90, no. I mean, it's so small it doesn't fit anymore. It's 91%. It gets much better. So it's a simple data set. If we train for more iterations, we'll get to 98, 99%, but you now see the idea of what it's doing. So now that we trained the network, we can use it. So now trained model is a trained network. Now we can take this model and make predictions. So we have our test set. I'm just going to pass it and say predict. These predictions are the Spark object. We can't really look inside it, so I'll say collect. And now these predictions is what actual numbers are. So if I look at the first 10 predictions, these are these numbers. So which may or may not be right, so let's check them out. In this function, I'm going to pick a random image, look at the prediction, and then look at the actual image. So 2 and 2, that looks good. 4 and 4, 4 and 4, 9 and 9. So I'm trying to find where we made a mistake. And since our accuracy is 92%, it might take a while before I get there. 2 and 2, 5, 5. There has to be a better way to do this. 8, 8, 9, 9, 7. Come on. I'm just not lucky.
Your model's too good.
No, but there you go, 8 and 1. Well, we know how good it is. It's 92%, so we are wrong about 10% of the time. So about every 10th image should be the wrong. So this one is 8. We thought it's 8, but it's actually 1. And we can probably see why. I have no idea how this is 8, but we can probably live with this error. So in this notebook, you can maybe write the function. I actually have this small exercise at home. There you go, and just more deterministically find all the errors and print them out and see what we predicted versus what the image looks like, and see where our mistakes make sense and where we could have done better. Well, this is it for me. Have any questions so far?
We can download these notebooks and try to run this.
Yes, if you took the image, you have to my GitHub, it has steps and says do this, do this, do that. If you use Docker, you can do that.
Is there a case scenario where instead of finding the image, you want to find the area that you're not, like cutting away, like Occam's razor? I'm thinking of when you're looking at cells, okay? And it's like you've got all this stuff in here, and so let me look at what, let me teach this not to look at this. How do I explain this?
Well, you look at the negative class, which is, well, basically you can detect objects, and once detecting objects, you can detect the other side of that.
Because that's gonna take much more resolution. Is this a regular cell, is this a cancerous cell, is this an...
I see what you're saying. So what you're talking about, people actually are doing that. I know actually there's a company working on diabetes diagnosis using the brain scans, MRI scans. Apparently diabetes shows up early in your brain scan, and right now it's like half art, half science. Well, it's science, but depending how trained the person who's looking at that is, they might detect, might not detect, they might have false positives, and so on and so forth. Since it's a computer vision problem, they basically have 10, 40, 50,000 scans of people who have diabetes, plus it's about same amount examples people who do not have. They train the network, and they're basically making predictions. So anything that you can express, actually a more interesting example of using computer image recognition is that, more I'm using the example I'd say recently. So there's a company working on recognizing how much it will take to fix a car by just taking the pictures of an accident. So they take an image of the car from all directions, they want to upload it and get the estimate. Of course it will be a very high level estimate because you don't see what's inside, but you kind of over time can guess that, depending on how crumpled it is, which parts have been hit and so on, you can guess like, $500, $2,000, $20,000, let's get into this category. And so they'll need a lot of images of damaged cars for that.
So I haven't tried the BigDL. I'm just wondering, so what does it buy you? So if you don't use BigDL and try to implement this problem,
What do you have? Like if you have your computer, right, you don't need BigDL. So you can use, well, you can't do much with a single computer, especially in large computer vision kind of problems, but you can use any other framework run it locally. Now, if you want to train on a lot of data, let's say you have 1 million images, so that's about 5 to 10 terabytes of just images, right? If you run it on your computer, it will take you months on the CPU. Now, you can build a GPU and run it in a single box on a GPU. Now it will take you, a week or two, and you're done. So, Spark, this BigDL is designed for large deployment. So now let's say you have hundreds terabytes of data, or petabytes of data, right? So, or even if you have a few terabytes of data, right? So how are you going to scale your machine learning?
No. What I'm referring to is I'm still using Spark ML. I'm just not using that.
So now using deep learning, yeah. So for this, you will need this once you want to do any deep learning kind of thing. So I'll give you an example. For example, you want to, so images is not, so you can apply deep learning models to various data sets for different purposes, right? It does have to be computer vision, it's just a more entertaining example. Once you want to use deep learning, there are no really deep learning libraries for Spark installations. You either have to write your own by hand, which why would you do that? Because you have BigDL. So once you have BigDL, it does two things. It gives a very simple API, as you can see in those files, like really one line at a time, and you build your network to use it. Two, it scales automatically. So if you have 4 node cluster, and you're going to start training, it's going to spray your data across all 4 nodes, across all the cores. If you have 8 cores each, you're going to have 32 effective cores working for you automatically with zero work on your hands. So you get things done, 32 times faster than you do it versus a single core. That's its value. So you already have this infrastructure sitting there, and I had that actual conversation, people coming to me saying, hey, we need to buy GPUs, so we need lots of money. I'm like, well, that conversation isn't going to go well with most people in the company in the CFO department. I'm like, well, why don't we use BigDL? Oh, great, we didn't know we had BigDL. So, and now we can use this infrastructure to run deep learning algorithms. So it's not always like what's better. If a GPU could be better in some cases, and if you have money, you don't care what to buy, maybe you'll buy it. But if you already have the infrastructure, or you're thinking, okay, I buy a GPU, but then it only applies to very specific workloads. It's useless for machine learning in general. You still need CPUs attached to it. It also has limited I/O. So if you need to start shoveling terabytes of data at it, it's gonna take you hours to just transfer data, so, and your GPU won't be doing much. So you're gonna might say, okay, you know what, I know a single CPU may be less powerful, but for the same amounts of money, I can buy a cluster, and then I can use for various tasks, including deep learning. So to me, that's the key kind of differentiator. I'm sure both of them have applications in their areas.
And I think she was also asking, so Spark ML is going to have really good libraries for things like random forest or GBTs or other approaches like that. And so, I mean, those are good, for certain types of problems. But, computer vision examples or other kinds of very highly dimensional data, deep learning is going to be very effective at those. So unstructured data and analysis, for example, natural language can be very effective at that. So again, if that's, and there's other, things that are working for you, that's good, but deep learning certainly has some areas where it would be able to outperform like the ensemble